Good afternoon everyone, and welcome to today's late exam answer video. Today I'm taking a look at a question covering fuel cells from the electropotential / electrochemical cells topic. In this particular fuel cell question, we're looking at a fuel cell that we don't specifically need to have learned any information for. So the spec says that you need to be aware of the hydrogen-oxygen fuel cell. You need to appreciate that it can be done in both acidic and alkaline conditions. You need to learn the half equations for the alkaline conditions. If it's the acidic conditions, they'll give you those. We need to be able to combine those together to give the overall equation, and we need to appreciate that the EMF will be the same, whether it's in acidic conditions or alkaline conditions, because the overall reaction occurring is the same. Here we're looking at a methanol oxygen fuel cell, so there's no expectation that we're going to know how to put the half equations together. So in parts A and B, they've given us sufficient information to put those half equations together, and it may be that we then have to join them together to give the overall. We don't here because that has been provided for us. We've also been provided with the EMF of the cell, and we're going to use that to calculate one of the standard electropotential values. Then we're going to think about why fuel cells do not need to be electrically recharged, and this is the main benefit of using a fuel cell. And then we're thinking about suggesting, and suggest questions are hard because you've got to think as logically as you possibly can. It's not something you will have been taught. It might be something that you happen to have discussed with your teacher in your class, but suggest questions, you've always got to assume that you don't know what the answer is, but you've got to use logic and, I guess, educated reasoning to try and figure out why, in this case, methanol is better than hydrogen in a fuel cell. So this is the question that I'm going to have a look at now for us. So we've got the overall reaction, and that in itself is quite helpful, because if we're writing the half equations for the two individual processes at the two electrodes, then we can look at those half equations and think, would they join together to give me that as my overall reaction equation? So we've got that, we've got the EMF, and I'll come back to that when we get onto part C. So first of all, we are told at the positive electrode that oxygen reacts with hydrogen ions to form water. So we've got enough information there to put together a half equation. So we're going to need oxygen, O2. We're going to need some amount of hydrogen ions, so H+, and then we're going to form water. Now, first thing we're going to need to do is balance our oxygen atoms. So we're going to need 2 lots of H2O being made. That gives me a total of 4 hydrogens now on the right hand side, so I'm going to need 4H+. And then the bit that sometimes can be forgotten in certainly writing half equations, thinking about fuel cells, is our electrons. But we're writing this half equation in exactly the same way we would consider writing any half equation. So we've balanced out our oxygen atoms by having water, we've balanced our H's by adding H+. Now we need to add electrons to balance out the charges. So I'm going to need 4 electrons on the left hand side to cancel out the 4 positive charges from the H+ ions, because the right hand side is neutral, there's no charge. Now, they've told us that's the positive electrode. One thing we need to remember with our electrochemical cells is that the positive electrode will always be on the right hand side. The positive electrode is always where reduction occurs. So that's another good thing that I've got my electrons on the left hand side, because that shows that electrons are being gained to form the water, and that's going to help us again in part C. So I'm just going to make a little note that the positive electrode will be on the right hand side. Looking at then part B, we're told that at the negative electrode that methanol reacts with water to produce carbon dioxide and hydrogen ions, and again we have to give the half equation for that reaction. Now the negative electrode is always the one on the left hand side of our cell, and that's where oxidation should be occurring. So again, that's a nice little check that we should have our electrons now appearing on the right hand side of our half equation, which makes sense because we've already got these ones on the left and the electrons would need to cancel to give us our overall equation. So methanol reacts with water, so CH3OH plus H2O, and that produces carbon dioxide and hydrogen ions, so CO2 plus H plus. So first step, balance everything that's not oxygen and hydrogen, which will be carbon. We've got 1 carbon in methanol, 1 carbon in our CO2, so that is already sorted. Then we've got 2 oxygens, 1 in the methanol, 1 in the water, and we've got 2 oxygens in the CO2. So the oxygens are sorted. So then it would be the hydrogens. Now we've got 1, 2, 3, 4 hydrogens here. So we're going to need 4 hydrogens on this side. Oh, no, we don't have 4 hydrogens at all. I was just thinking that can't be right. We've got 3 there. 3, 4, 5, 6. Okay, that's some awful maths there by me. I'm very sorry. So yeah, we'll turn that into a 6. And therefore, to balance the charges, I'm going to need 6 electrons on this right-hand side. Now, as I said before, the reason why I paused before I recounted my hydrogens was because I was looking at the 2 half equations and thinking, well, if it was 4 H pluses and thus 4 electrons, I'd have all of those cancelling, and then I'd be adding this, 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 and then this and this on the right-hand side. And I was like, that's not going to work because I'm going to lose the water here, and that's going to drop to 1, which wouldn't be right. I wouldn't have enough oxygens on the left-hand side, and I was starting to panic, and then I realised that I'd miscounted my hydrogen in the methanol. So yeah, we've got 6 hydrogen ions that we need on the right hand side and 6 electrons. So if we were then combining those together, we'd have to find the lowest common multiple of 4 and 6, which is going to be 12, times everything in this equation by 3, times everything in this equation by 2, and then cancel out the electrons, simplify anything else that we can simplify, so we can get rid of the H pluses, we can cancel out some of the waters, and then simplify that to get the equation that's given there. So I knew I'd done something wrong and I just couldn't count, which is very standard for me. Okay, so we've got our half equations done. Now we can have a think about part C that says the standard electropotential for the CO2 CH3OH electrode is plus 0.03 volts. Now that equation, electrode is on the left hand side, that's our negative electrode, so that 0.03 volts, when we work out the EMF and we do right minus left to get EMF, we're going to do the right that we're trying to work out minus 0.03, and that's going to give me my EMF that we were given up there of 1.2. So 1.20 is equal to the standard electropotential for the right hand side minus 0.03. So therefore the standard electropotential value for the right hand side is got to be equal to 1.23 volts. And that becomes an easy question if you know which side that this is going on. And again, they had to give us some information to be able to know whether that was going to be the E0 value for the right hand side or the left hand side. And they did that by telling us that the reaction we wrote in part A was our positive electrode, reaction we wrote in part B, that would occur at our negative electrode. So that is then the standard electropotential value for the right hand side, and that does not need voltage as its units because that is a standard electropotential value. There we go, get rid of that. In terms of part D, state why a fuel cell does not need to be electrically recharged. what we can do with our fuel cells is constantly supply the fuel and oxygen. And if we do that and we continually just add more methanol and we keep adding more oxygen, the reaction can just keep going and going and going and going, and thus the cell does not need to be recharged. When we think about both non-rechargeable and rechargeable cells, there'll be a point where we run out of the species that's being oxidized and or the species that's being reduced. And for rechargeable cells, when you plug them into the mains, it forces the reaction to go the other way round, so that you then gain back those reactants. That's the major benefit of a fuel cell. So the methanol, which is the fuel, and oxygen, which is the oxidant, can be constantly supplied. And if we were then to think about what the graph of sort of EMF against time would look like for a fuel cell, it would be a horizontal flat line like that, because the voltage that we can generate from a fuel cell is the same because we are constantly supplying the fuel and oxygen. Whereas in a non-rechargeable or even a rechargeable cell, there'll be a point where the cell is dead and has no EMF, but then with the rechargeable ones we can then build that back up again when we plug it into the mains. So those sorts of sketch graph looks very different. Now, one thing we do need to be aware of with the hydrogen fuel cell is hydrogen is hard to store because it's a gas. It's reactive, explosive. Storing hydrogen gas quite high pressure is very hard to do. It's not very safe. Whereas methanol, as we can see in the equation at the top, which is, in my opinion, one of the key reasons that they've given it to us, we can see that the methanol is a liquid. And it is therefore going to be easier and safer to store the methanol as a liquid than it would be to store the hydrogen as a gas. Now, like I said before, that is a suggest question. So something that, yeah, you've got to kind of look at what you've been told and can you piece something together. Now, if it had said what's a disadvantage, we'd be thinking about potentially the fact that this fuel cell will release CO2, whereas if we're using the hydrogen fuel cell, the only product is water, and that's a major plus point for the hydrogen fuel cell. However, it didn't say disadvantage, it said advantage, so we have to just use our knowledge of the hydrogen fuel cell, have a look at what we've been told about the methanol fuel cell, and see what we can put together. So in this case, methanol is a liquid which is easier and safer to store than hydrogen gas. And that's our question. Now, I have seen them ask about other types of fuel cells as well. There's a question that's been about a glucose oxygen fuel cell. We could also have them with hydrocarbons as well, or ethanol, which would be obviously very similar to methanol. So yeah, as well as obviously making sure that we know the hydrogen fuel cell example, it's also good that we know some of the key features of fuel cells generally so that we can apply those key points to other types of fuel cells. Apologies again for my miscounting and adding volts here that we didn't need. That never happened. And if anyone has any questions about what I've done there, as always guys, please just let me know. Thank you so much for watching, and I hope you have a really lovely end of your week.